This unit focuses on laying out the terms that we use to describe the relative strengths of different acids. In the earlier segment, we talked about the different definitions of acids and bases, ranging from the Arrhenius acid and base to the Bronsted-Lowry and the Lewis acid and Lewis base. Now what we're going to do is look at, once we've defined molecules as acids, for example, how can we define how strong the acid is? And when we think of a strong acid, or a strong base for that matter, when we just describe something as being a strong acid or a strong base, the term that we can use to think about this conceptually is we can think of a strong acid or a strong base as being a highly reactive acid or a highly reactive base. In other words, a molecule that is very eager to react, a molecule for which the reaction will generally be very complete and go with an equilibrium that's very far toward the side of the product. So when we think of strong, be thinking in your mind of strong equals that the acid is going to be very prone to reacting completely. So when we look at acids and bases and we try to assess the strength of those molecules or how reactive they are, how prone to reacting they are, how prone an acid is to donating a proton, the terminology that we use to describe the strengths of acids is the pKa value. So the pKa value is going to be our measure of acid strength. And back when you took general chemistry, you may recall having learned a bunch of different equations for defining pKa and rigorously calculating K equilibrium constants or acid dissociation constants and things like that. In organic chemistry, we're going to take a much more qualitative approach to this. So there's nothing in this chapter, or really any chapter, that you will need a calculator for. Instead, we're going to be trying to look qualitatively at the different acid strengths in order to assess what molecule in a reaction mixture, for example, is the most reactive or the strongest acid out of the reaction mixture. So when we refer to pK as a measure of acid strength, when we think about pK and how it relates to acid strength, the lower the pKa value, the stronger the acid. So lower pKa corresponds to a stronger acid or a more reactive acid. When we talk about a more reactive acid or a stronger acid, that means that the reaction equilibrium of that molecule with a base is going to lie further toward the side of the product. It's going to be more prone to react to give more product at equilibrium. So lower pKa corresponds to a stronger acid, and it's going to refer to a reaction equilibrium when the acid reacts with the base, where that equilibrium lies further toward the product side. So in other words, further toward the right-hand side of the equation. So if we take as an example here, as our acid, HA, I'm using that HA because for the Bronsted-Lowry definition and the Arrhenius definition, we needed a proton involved. We're going to take our base, which we'll just plug in as B, and I'll use a lone pair of electrons there on B and our equilibrium arrow to show what's going on here. I'm also going to make B an anion here. And remember that the reason I'm showing the base here as having a lone pair of electrons is that's a prerequisite for something to act as a base. It has to have either a lone pair of electrons or a pi bond. So we're bringing in our base. Our base, by the Arrhenius definition or the Bronsted-Lowry definition, is going to grab a proton from the acid. That forces the bond between H and A to break to avoid going over the octet rule. And then our product of this reaction, we're using generic terms here to define our base and our acid. So our base B formed a new bond to the proton H. So we'll go ahead and fill that in. And we also need to go ahead and fill in A. So we'll do plus A. And our A from HA, our acid, is going to have a lone pair of electrons now because it picked those up from the covalent bond that broke where the electrons went on to the acid. And we'll go ahead and plug a negative formal charge in there because it picked up a couple of extra electrons from that covalent bond breaking. Now it has possession of an extra electron, and so it's going to take on a negative formal charge. That will also let us balance the charge between reactant and product here. So our acid, again, was defined as HA because that's our proton donor. Base was what's accepting the proton, and then our conjugate acid on the right-hand side, I'll put a Ca because that's what gained a proton during the course of the reaction. If we went back toward the left-hand side, it would be losing a proton. and our conjugate base here is what has lost a proton during the course of the reaction. So when we look at this equation, the lower the pKa value of our acid, the further this equilibrium will lie toward the right-hand side. In other words, the more of BH and the A anion that we would expect to have at equilibrium. And so when we're looking at the different pKa values for molecules, we can use that as a relative assessment of the different strengths of the acids. And we can pull up a table of that information. So we take a look at this table. This table is directly from the Wade textbook. And we take a look at the relative strengths of some common different organic acids and inorganic acids. If we look here at the column of the table that lists the acid, in pink is the proton that is lost during the course of the reaction. And in each case, we're reacting with water to give an equilibrium reaction. So we have that equilibrium arrow there that is common for acid-base reactions. And then we show on the right-hand side of the arrow our conjugate acid and conjugate base. We have our acid reacting with our base, which water was used here, to give our conjugate acid, which is what's picked up a proton, and our conjugate base, which is what lost a proton during the course of the reaction. So HCl became Cl-. So that's the trend all the way down here as we've listed our acid base, acid, conjugate base. And what you'll notice here is that we have a list of the pKa values. That list of pKa values is all the way over here at the right-hand side, and that is referring to the pKa value for the acid. So the acid pKa value is listed over here. And certainly my expectation is never for you to memorize these pKa tables. If you have a problem where you would need to know the exact value of pKa, it would be given to you. So it's not a useful expenditure of your time and mental capacities to memorize these values. You can always look them up in the book. What we are going to learn in the next unit is for molecules that go beyond this table where we don't have a pKa value readily available in the literature, how could we predict how acidic or non-acidic a particular molecule is? So we will learn some guidelines for that to make predictions of relative pKa values, but I'm never going to expect you to memorize these absolute numbers. So in this table, what we have ranked is we've started with the strongest acid at the top. That means that the equilibrium for these reactions is going to be furthest to the right because they're each reacting with the same base, water, so the base is the constant there. And in reacting with that base, they go to give the conjugate acid and conjugate base. As we go down the table, we get to weaker and weaker acids. And as we get down to the stuff that's listed as very weak or not acidic, that's going to have the equilibrium of the reaction lying furthest toward the left-hand side. In other words, we would describe methane as being very non-reactive as an acid. It's a very, very, very weak acid. So the equilibrium here at the bottom would be furthest to the left-hand side of the equation. So another assessment that we can make out of this table of different pKa values is that if we start off with a relatively strong reactive acid, we react it with a particular base, such as water in this case, and we look at the conjugate acid and conjugate base product that forms here. In this table, the variable is the conjugate base. The conjugate acid is always H3O+. If we look at those conjugate bases, we can rank those conjugate bases in order from most stable to least stable. We're at the top of the chart here is going to correspond to the conjugate bases that are most stable. So in addition to the pKa value, giving us information about the relative strength or stability of the acid, it also gives us information about the relative strength or stability of the conjugate base, the deprotonated form of the acid. So once the acid has lost a proton, if we look down here at the bottom, the CH4, once it lost a proton, became CH3-, and we can assess that that CH3- is extremely unstable because of the fact that it corresponds to a relatively strong acid. On the other hand, Cl- is very, very stable. And you probably know that intuitively because if you take a look at the sodium chloride, for example, that might be in your kitchen, you don't typically think of sodium chloride as something that's highly explosive or going to detonate on your kitchen table at any given time. So we can certainly assess that based on instinct, should be relatively stable. So what's going to happen here as a trend that we can overall see is that strong acids are going to give way to very stable conjugate bases. That's what we see illustrated up at the top here. So strong acids are going to give way to very, very stable conjugate bases, and the equilibrium is going to lie very far toward the side of that conjugate base because of the fact that the conjugate base is very stable, and these acid-base reactions really want to favor stability as much as possible. On the flip side of the coin, if we come down here to the bottom of the table, this situation is going to correspond to the starting material, such as methane, being very stable, very unreactive as an acid, and hence it's going to prefer to just stay like that. So the equilibrium is going to be very, very far toward the left-hand side of the equation, because in fact, if that methane donated a proton and gave our methyl anion, that methyl anion is very, very unstable because carbon isn't particularly happy to carry around a negative formal charge. Carbon is not a very electronegative atom, and so when you put a negative formal charge on it, it's not particularly adept at carrying around that negative formal charge. And so as a result, this reaction, the reactions at the bottom of this chart are pretty much a no-go. The equilibrium is going to lie very, very, very far toward the side of the reactant. So if we want to draw the equilibrium error somewhat accurately, down here like I'm highlighting in red, rather than showing that as an equilibrium error that's equal to both sides, we could really show that the reaction is very, very, very predominantly toward the left-hand side and just tiny, tiny bits toward the right-hand side. On the other hand, at the top here, where we have a really strong acid, the strong acid equilibrium is going to be very, very far toward the side of the product with very, very little reaction in the backward direction. So at equilibrium, we have tons and tons of chloride anion, very little HCl left. So let's write down a few of these things in words to just summarize what we've been discussing here. So to recap this, information from our table, anytime we have a strong acid, what's going to be the case is that the strong acids we can think of as being highly reactive, and they're going to yield a highly stable conjugate base. So it's like there's two sides to this equation. One side is going to be a very stable side, one side is a very unstable side, and the side that is preferable is that lazy, stable side. Molecules, much like a lot of humans, tend to be in the lowest energy state possible, tend to favor a stable state rather than a high energy state. And so what's going to happen is the strong acids are going to generally react. They're going to yield a very stable conjugate base, and the equilibrium is going to be very far toward the side of the products. So there's going to be lots and lots of product and very little of the acid starting material left at equilibrium. On the other hand, a weak acid, that would be molecules that have a high pKa. Strong acids have a low pKa. So the lower the pKa, the stronger the acid, the more reactive the acid. Weak acids, on the flip side, are going to have a higher pKa value. And that higher pKa value is going to correspond to a lower reactivity. In other words, they're not super eager to donate a proton. And they're going to give way to a highly unstable conjugate base. So we can go down the list there of the items in that table above and look at those conjugate bases, and we can say that if we're looking at the conjugate bases, we're going from the most stable conjugate base at the top. As we go down, we're going to less and less stable conjugate bases. And by the way, when we're talking about conjugate bases, you could also throw out the term just base when we're looking at base strength. The strongest base is the least stable base. The strongest acid is the least stable acid. So the stability is what we're going to be looking at here. And with weak acids, to finish off this bullet point list here, to compare them to strong acids, for weak acids, the equilibrium is going to lie toward the side of the reactant. very little of the conjugate base product would be present at equilibrium typically if we're reacting with water, as we saw in the table above. So with that, definitions of conjugate acid, conjugate base, and a little bit of information about the pKa values of molecules and the strengths of acids, what we'll do in the next segment is we'll learn ways to qualitatively predict acid strength, whether an acid will be a strong acid or a weak acid, without having to have this pKa table in front of you, because for the vast majority of compounds that we're going to be looking at this semester, you won't have access to a pKa table that perfectly matches the compound that you're looking at. Instead, you will need some guidelines for coming up with the relative strengths of different acids. So that's what we'll do in the next segment.